Hey guys, welcome to the Biomechanics 1 video series, looking at part 2 concerned with angular velocity. Right, so angular velocity gives us an idea of how quickly something tends to rotate or how quickly it's changing its angular position. So by definition, angular velocity can be defined as the time rate of change of angular position, right? So it's the time rate of change of angular position. And can be defined mathematically by this Greek letter omega, right? Which is equal to some change in angular position divided by some change in time. So in our previous video, we looked at what this change in angular position is, this delta theta, where delta theta is equal to some final angular position minus some initial angular position. It can be positive or negative or zero, right, depending on which direction I moved in or rotated in. Remember we said that clockwise is typically negative and anti-clockwise is typically positive. This delta t, delta time, is always some positive value, right? So omega picks up the sign of delta theta. What is the SI unit of angular velocity? Well, it is the unit in which this angular position is measured in, which we discussed in a previous video is the radian, divided by the unit in which time is typically measured in, which is the second, right? So the SI unit for angular velocity is in radians per second. Okay, that is the given convention. And notice how this is analogous to velocity, right? Where velocity is some change in linear position divided by some change in time. And we'll look at what the link is between these two in our fourth video. Another important characteristic of angular velocity is that angular velocity is the slope of a angular position versus time graph, right? The same way that linear velocity was the slope of a linear displacement versus time graph, the same principles apply here. So say, for example, I had some angular displacement versus time graph that looked something like this, where at, say, for example, 1 second, the person was at 2 radians, and at 2 seconds, the person was at 4 radians, that's a 4, and at 3 seconds, the person was at 6 radians. Right, that's how they tended to rotate. So how would I calculate the slope? Well, remember that the slope is equal to the rise divided by the run, right? So since we can see that this is a straight line graph, I can kind of take the slope anywhere. So let's take it between these two positions here towards the end. Let's use a different color. So if I want to find the slope over here, I would look at this change in the rise over this change in the time factor. That's supposed to be 3 seconds. So the slope between seconds 2 and 3, remember that this would be my final position and this is my end position, since it's some time ahead or some point in time forward of where I started in this particular analysis. So that my change in the rise, denoted by this change in theta, is equal to some final position minus some initial position. So my final angular position was 6 radians minus 4 radians, and this change in time was, well, 3 seconds minus 2 seconds, which gives me 2/1 radians per second, right, or 2 radians per second. And that would be true regardless of where I decide to take the slope. So let's just prove that quickly and just say what the slope is down here. So again, it will be some change in position over some change in time. My final position in this case now becomes this endpoint here, and this is my initial position. So my final angular position in that analysis is 4. My initial was 2. The change in time was 2 seconds minus 1 second. And again, I sit with 2 over 1 radians per second. Notice again that the slope is a positive value, meaning I was rotating in an anti-clockwise direction in this case, right? Okay. So if I had to kind of plot this on a angular velocity versus time graph, the data that I've just derived or calculated from here. So at 1 second, at 2 seconds, at 3 seconds, you would find that it is constantly staying at this 2 radians per second mark. Which brings me to a important, very, very important concept, that if it's true that the slope of a position versus time graph gives me the angular velocity, then there must be some way in which I can get the angular position from a angular velocity versus time graph. And that, in actual fact, ends up being the area under a angular velocity versus time graph. So if I have my angular velocity being my change in angular position divided by my change in time, if I wanted to isolate this, I could multiply that out. So that says that my change in angular position is equal to my angular velocity times my change in time. Okay. So in essence, what this ends up being is the area of a angular velocity versus time graph, right? And you'll see why. I'll prove now that it is true. But you can see here, after 3 seconds, this person had rotated through 6 radians, right? In 2 seconds, the person has rotated through 4 radians, and in 1 second, the person had rotated through 2 radians, right? So that's the position at that point in time. So if this is true in terms of being the area under a angular velocity versus time graph, let's see if that's what we get. So after 1 second, right, if I had to calculate the area within this, it would give me my change in angular position. So area typically is calculated as the base times the height, which in our case, the length of our base over here is just 1 unit or 1 second, times the height, which is 2, which gives me 2 radians. So it's saying that after 1 second, I should have been at the 2 radian mark. Well, that's kind of true. So this model is looking pretty accurate so far. Let's see if I kind of add the next one. So I say after 2 seconds, how far should this object have rotated? So now my base becomes, or my area becomes all of this. So area 2 is then equal to the base times the height, so 2 times 2, which is equal to 4 radians. Let's see if that's right. So after 2 seconds, I should have been at the 4 radian mark. So this is looking pretty good so far. Let's try and see if I can hold that with the third and final one. So after 3 seconds, where should this angular position have been? So now all of a sudden, this whole area here, I need to factor in. So area number 3, after 3 seconds, is equal to base, which is 3, height is still 2, and I get 6 radians. So after 3 seconds, I should have covered 6 radians. And you can try the same calculation with the linear displacement and linear velocity calculation. You should get the exact same values. Okay. Well, let's try this in a concept test quickly. Right, so based on a position versus time graph, find the angular velocity at time is equal to 4 seconds. You have 5 options. Is it 1 radian per second, 1/3 of a radian per second, 2 radians per second, 0.75, or 3/4 of a radian per second, or half radian per second? I encourage you to pause it, try and calculate it, and see what answer you come up with. Okay, so the correct answer should be B. So since this is a straight line graph, we should know by now that I could take the slope at any point in time, and the velocity, or angular velocity in this case, will be the same at any point along this graph. So if I just had to kind of project this out, so the slope is equal to rise over run. Well, this is my rise over here, and this is my run over here, which is equal to some final position minus some initial position. So that is 3 minus 1 divided by 6 minus 0, which gives me 2/6, or 1/3 radians per second, right? So what was the angular velocity at time is equal to 4 seconds? Well, it's the same all the way throughout. So angular velocity at time is equal to 4 seconds is 1/3 of a radian per second. Okay, and that should be your answer. Let's try this third one. Based on the graph below, which position or which option best represents the angular velocity versus time graph? So if this is how something is rotating, it's a curved path, which one of these 4 options, A, B, C, or D, best represents the angular velocity versus time graph? So give it a pause, see if you can work your way through it, and then we'll get the answer. Okay, so the correct answer in this case is option A. Remember that even if it's a curved path, we can find out what the angular velocity is at any point in time by taking the slope at that point in time. So what you guys will notice is that at any particular point in time, the slope seems to be constantly decreasing, right? We had a similar graph when we looked at the linear components. Remember that slope is just giving me some number, right? Is equal to one number. So in this initial position over here, it is quite a steep slope, which means a steep slope kind of equates to a larger number. Whereas a slightly less steep slope equals smaller number, right? So steepness gives you an idea of the magnitude of that number, the size of that number, right? So what you'll see is initially it must have been a high number, and then it constantly starts to decrease. And remember, the slope of a top line, or the straight line, is 0. So at the end of this particular analysis, the value should have been 0. In this instance, the numbers are getting bigger and bigger and bigger, as opposed to smaller and smaller and smaller, so that can't be it. The same is true for option number C. And with option number D, it's saying that it is constant, which would have been true if I had a position versus time graph that looked like that. If I had to take the slope of this, I would get the same number regardless of which point in time I'm assessing and analyzing. So that would have been true if it was a straight line graph. But in a curved graph, it was getting smaller and smaller and smaller, and ultimately going down to 0, which means it was probably slowing down, right? It was constantly being decelerated, which is something we'll look at in the next video when we look at angular acceleration. Good. Hope you guys enjoyed that. Hope you guys learned a lot. And again, work your way through the biomechanics manual. There should be lots of examples for you guys to work through. And if you guys still get stuck, then you can always ask me questions. All right, all the best.